Last time we saw how to design a lead compensator, and that lead compensator is basically a high pass filter, and this was the transfer function for it, and we learned how to determine the constant K or Kc, alpha, and T based on the requirement of the system. And we also learned, if you remember, that lead compensator has the property that it improves transient response, but does not do much about steady state. And it can basically magnify high frequency noise. Lag, the one that we are going to work on right now, on the other hand, acts like a low pass filter, and it will help reducing the effects of noise, improves the steady state accuracy, but it makes the system slower and a little bit less stable. And if we want everything, we combine. So first, let's see how we design lag compensator, and then how we do a lag lead, or you can call lead lag compensator. So if you remember, a lag compensator from the chapter 6 Ruth Lucas, it has a transfer function like this: Kc times s plus 1 over t divided by s plus 1 over beta t, where beta was bigger than 1. And if you multiply both numerator and denominator by beta t, that's another way to describe the compensator transfer function. And again, the reason we do it this way is because when we do Bode plots, we want the constants in numerator and denominator to be 1, where here k is Kc times beta. This is the Nyquist plot for it, which is kind of similar to the lead, but with a mirror image, right? So this is kind of like a semicircle above real axis. This looks like a semicircle below the real axis, but the more important thing is the Bode plot for it, which clearly shows that it basically allows low frequencies to pass by, while for high frequencies it tries to attenuate. So it is a low pass filter. Okay, that's what it is. It acts quite like a PI controller or I controller. And so when we want to design a lag compensator, there are several steps that we have to take, and these steps quite very similar to the steps we took to design a lead compensator. So the first stage is based on the static error constants, typically kV. We determine the constant K, this constant, to make that much of change in kV value most of the times. And then we redraw the Bode plot of the gain modified system. So if we define G1 to be K times G, we draw the Bode plot of G1, and then we determine the frequency in G1 at which the phase of G1 is negative 180 plus phase margin. And typically we add 5 to 12 degrees to phase margin for safety. So if the problem says 40-degree phase margin minimum, we add 5 to 12 degrees on the top of that 40, make it like 45, 50, and then we find the frequency in G1 at which the phase is negative 180 plus that 50, so it's like negative 130 or something like that. Then, now that we found this frequency, the next step is to determine parameter T. Now, I told you that the lag compensator will make the system slow. To minimize this detrimental effect, what we do, we try to make the pole and the zero of the lag compensator at frequencies that are significantly lower than this frequency, than this gain crossover frequency that we found in step number 2. So whatever frequency we found in step number 2, let's say, for example, 10 radians per second, to be the new gain crossover frequency, we make sure the zero and the pole of this transfer function, which are at 1 over t and 1 over beta t with negative sign, we make sure they are at frequencies quite lower than this frequency we found in step number 2. Typically, we go 1 octave to 1 decade below. For example, again, if the frequency we found in step number 2 is 10 radians per second, 1 decade below that is 1 radian per second, and then that can give us the new zero of the lag compensator, right? So the zero of the lag compensator is at 1 over t. So we make sure this 1 over t is at 1 decade below it, like at 1 radians, then we determine t based on that. Okay, so it says 1 octave to 1 decade. To be conservative, we typically go 1 decade. Now that we got k and t, the next parameter is beta. And to find beta, we use the frequency we found in step number 2, and at that frequency, we calculate the magnitude of G1. Then, since the lag compensator can bring down the amplitude, the magnitude, by 20 log of beta at this gain crossover frequency, we set that equal to 20 log beta, and from there we can find beta. So now that we learned how to determine the value of these 3 parameters, let's go ahead and go over this example together. Now, one thing I need to mention is, again, the lag compensator removes high noises. It is a low-pass filter, and it kind of acts like a PI controller, which can make a system unstable or less stable at least. To avoid this undesirable effect, we make sure that the T of the compensator, which is basically reciprocal of the zero of the compensator, is quite larger than the largest time constant of the system. For example, in this problem that we are going to solve, if we can find the time constant of this GS, the system with GS, and let's say that time constant is 2 seconds, then we make sure the T that we set for the compensator is quite bigger than 2, okay? Maybe by order of magnitude. So we go from 2 to 20 or something, or at least 5 times bigger, 10. So that makes this compensator effect on stability minimal. The other thing, again, since the lag compensator moves the gain crossover frequency to lower frequencies, so it reduces the bandwidth of the system and makes the transient response slower. So 2 big drawbacks of a lag compensator. The best thing about it is it improves steady state response and removes the effect of noise, but it can make the system less stable and slower. So we have to basically choose a strategy later that whenever we want to design a compensator, if we can achieve the same goals using either a lag or a lead, which one we should go for, right? Because lead has good things. It makes system more stable and faster, but it is susceptible to noise, and it does not significantly affect the steady state error. This one is quite the opposite. So first, let's go through this example together. And here we have this transfer function, 1 over s times s plus 1 times 0.5 s plus 1. We want KV to go to 5, phase margin minimal 40 degrees, and 10 decibel minimal gain margin. And what do? We go according to these steps. Step number 1, find this constant K such that KV of the new system is the number that you want it to be, 5. The original system, this system does not have a KV of 5. We're going to calculate it. It's less than 5. We want to bump it up to 5 to reduce the steady state error. So if you look here, GS, which is 1 over S times S plus 1 times 0.5 S plus 1, KV for this, it is equal to the limit of S times GS as S goes to 0, and that S and this S would cancel out, so and these S's go to 0, so you're gonna get 1 over 1 or 1 unit. So, okay, that's your KV. Now, on the other hand, if you consider a new transfer function, G1, which is K times G, okay, so it has the same denominator, but the numerator is K instead of 1. If you calculate KV for this system, which is the original one, plus a compensator, which is only a gain, now here, you see it is going to be equal to K, and this should be 5. Therefore, you choose your compensator gain K to be 5. That will take care of the steady state error. What else? Now, we need to shift phase margin to 40 degrees, right? If I just go ahead and basically plot for you the phase and the gain of the system G1, which is K times G or 5 times G. If we do that, first let's see how much is phase and gain margin for this system. That's the only thing we did to it, we added a gain. First let's look at it, then we come back and see what we should do about it. So first thing is, here, let me clear this stuff and redo it for you. So we say the transfer function is 5, which is numerator, and denominator is convolution of S times S plus 1, which is 1, 1, 0, and then 0.5 and 1, 0.5 S and 1. So that's my system. And then I define a fine array of frequencies, and then I plot my body with it, and I can even add the grid on if I want. And now let's find the phase and gain margin of system G1, then we'll discuss. Just as a practice. So if I click on data tip, hopefully it brings it up, yes. How would you find the phase margin? Phase margin is where first find the frequency at which the gain is 0. And I guess this is the closest you can get to 0. So the gain crossover frequency is 1.8. Then you find the phase of the system at that location. Let's go exactly to 1.8 again. And you see it's negative 193. So how much is the phase margin of the system here? If you remember, the phase margin is this angle, whatever it is that you found, plus 180, right? Which is going to be negative 13 degrees. What does it mean? You remember, negative phase margin means what? Means the system G1 is unstable actually, right? We need both positive gain and phase margin to be stable. This system has negative phase margin. Now let's also determine the gain margin. For the gain margin, we need to find the frequency at which the phase becomes negative 180, and hopefully it allows me to find this point. So here we find the frequency at which the phase is negative 180, which is roughly here. That's about 1.41, and then at that position we find the magnitude, and then the negative of this magnitude is the gain margin, right? So if you see now, the gain margin is what? Negative 4.45 decibel. And so gain margin is also negative. That's another indication that this system is not stable. So yes, we could make the steady state error to go down, but this system is not stable. So we have to do a lot more to make this system work. And to do so, now we need a frequency in G1 at which the phase of the system is negative 180 plus the required phase margin plus an extra 5 to 12 degrees to compensate for the negative effects of the lag compensator. So what we want in this example is 40 minimal. So we add 40 to negative 180, and then we go any angle between 5 to 12. 12 is the maximum conservative solution. Let's this time choose that one. So we want to know at what frequency the phase of G1 of J omega is equal to negative 180 plus 40 plus 12, which is negative 128 degrees. Okay, let's find this frequency. So here, let me redo that plot for you, and now we go and find the place with negative 128 in phase. So here we come somewhere around let's say about 0.46, right? So at 0.46, the angle is negative 128. So I can choose 0.46 or something like that. And then, so this frequency was 0.46. And then I make sure that the zero of the compensator, which is located at 1 over T, is somewhere between 1 octave to 1 decade below this number. So how much is 1 decade or 1 octave below this? So 0.46, if I go 1 octave below, means what? Means I go from this frequency to half of it. If it's 1 octave above, means twice as much. So it is going to be 0.23, right? If I want to go 1 decade below, what does it mean? Means go to 10 times smaller. 1 decade above means go to 10 times bigger. So that is going to be 0.046. So it should be somewhere in this range, below this number or below that number. And your textbook, if you look, your textbook chose this 1 over T to be 0.1. Because from here you can calculate T equal 10, and I guess your textbook wanted a nice number. So that's why they probably chose 0.1. So T is 10. Okay, so that's the number for T. This was the number for K. And now let's see how we calculate beta. So to calculate beta, it says find the magnitude of G1 at that frequency we found in step number 2, which was 0.46. Find the magnitude at that frequency and set it equal to 20 log of beta, and that way you determine beta. So at this frequency, of 0.6, how much is magnitude? So let's find it. So it is here or somewhere close. Oh, sorry. Let's see. That number should exactly be clickable. So it is about 19.7, 19.8. Okay, so this 19.7 decibel should be equal to 20 log of beta. And therefore, if you calculate beta, you see beta is almost 10, a little smaller than 10. So your textbook approximated it by 10. Again, probably looking for a nice number. It's less than 10, it's a little less than 10, but your textbook rounded it to 10. So now I have beta, I have T, I have K, and my compensator is completely determined, right? My compensator is, of course, Kc times S plus 1 over T, or you can say it's K, 1 plus St, 1 plus S beta T. So if I want to write it here, my compensator Gc is, again, I write it for you here. So this guy was 5, T was 10, beta was also 10. So this is your compensator. And now you put that in series with your original G. So this GC times G becomes your new G. And if we look at this new G, let's see if this new G has the desired phase and gain margin, right? It definitely has the KV, because if you let S go to 0 for this system, multiplied by the original G, you clearly see it's 5. But let's look at the phase and gain margin of that. So we want to multiply this whole thing by the original G, which is this one, right? So the new G, if I want to write it, G new, it is going to be 50S plus 5 divided by 100S plus 1. This is multiplied by 1 over S times S plus 1 times 0.5 S plus 1. Okay, let's look at the Bode plot for this G of new. So here, this is GC, 55, 101. And then we have the original G, which is, of course, this one, right? 1 and convolution of that. And then we say G new is equal to series of G and GC. And then we say, we define our frequency range. And then we do a Bode plot. And we can turn the grid on if you want. And now let's take a look. So you can always find it from here. That tool does not show up well. And first, where is it that gain is 0? So I guess this is the closest you can get to 0. And then at 0.445, we try to find the phase of the system, which is negative 138. And now if I add this negative 148 to positive 180, what do I get? Yes, the phase margin is 180 or negative 138 plus 180, which is 42. So you see, I added 12 extra degrees to the required phase margin of 40. So I was shooting for 52 degrees phase margin, but what I got is 42, right? Because this lag compensator shifts the gain crossover frequency. But still, this is more than 50 that I wanted, so I'm good. And then I also go ahead and find where the phase becomes negative 180. First, let me move this around and then find this point, and that's 1.32. And then I come here and at the same frequency I find the gain, which is 14.4. So the gain margin is negative of that number, right? So the gain margin is 14.4 decibel, which is more than the original, I assume 12, right? It was 10 decibels. So I got both of them covered. Okay, so this was how we design a lag compensator. Now it is time to look at a lead lag, the combination. So a lead lag, just like what you learned in the previous chapter, is a combination of lead and lag. It has a lead portion, it has a lag portion. It has two parameters, gamma and beta. This gamma is like a reciprocal of alpha that you saw in the lead compensator formula, right? This alpha that you saw less than 1, this gamma that you see is exactly reciprocal of that. So it's not really much different. And I could use alpha here, but your textbook prefers both of these parameters to be bigger than 1 instead of beta bigger and alpha less than 1. So it is redefining parameter alpha into a new parameter gamma. But this is the lead portion, the lag portion, the gain. This is the Nyquist plot, which is like a full circle. And this is more important, the Bode plot, which you can see it doesn't have attenuation at some range of frequencies. Then for some mid-range frequency, it has attenuation. And again, on high frequency, it does not have attenuation. So what we call this is, we call it the band pass filter. So some areas it does do attenuation, and some areas in between, not at the two extremes, low or high, in mid-range, it does kill that signal. Okay, so it kills mid-range frequency signals and passes low and high. So it's to suppress that range of frequency, mid-range, that we don't want. So we call this a band pass filter. Of course, it has one order higher than lead and lag, which means a little less stable system, but it combines the advantages of both. If you can keep it stable, it improves both transient and steady state response together. The frequency at which the phase of the system, if you look at the phase, that's quite interesting. It starts at 0. In some portion, it reduces phase. In some portion, it contributes to phase and ultimately goes back to 0. And this inflection point where the phase goes back to 0 again, that happens at frequency of omega equal 1 over square root T1, T2, where T1 and T2 are the reciprocal of zeros of lead and lag portion. Okay, now how do we design the lead lag compensator? Well, we have 5 parameters to choose, T1, T2, Kc, gamma, and beta. And here, for simplicity, we assume beta is equal to gamma, so we reduce them down to 4 parameters. And in your textbook, this procedure is not exactly and explicitly mentioned. It just mentioned that it is a combination of lead and lag, while actually the lag has its own procedure, 5 steps, and the lead has its own procedure, 6 steps, and how to combine them exactly is not mentioned. It's quite vague. So what I did, I went through the examples and I made sure that I write for you the process like this, which you can easily follow and design the lead lag compensator. So stage number 1 is like what we had before. Make sure the gain K okay, or KC in this case, it is chosen such that the modified system, the gain modified system, does show the required static error constant. Okay, this is just like what we had in the past, no difference. And then draw the Bode plot of this new gain modified system G1, okay, and evaluate the phase margin. Okay, so we'll do that. And I can even get rid of this part. I don't think I need that portion. So I'm just trying to clean it and make it as nice as possible. So first thing is, for the example that we are going to solve, G is 1 over S times S plus 1 times S plus 2. And we need KB of 10, phase margin of 50, and gain margin of 10 decibels. So if we go and look for this system, G is equal to 1 over S times S plus 1 times S plus 2. And KV is the limit of SGS as S goes to 0, which in this case you see is 1/2. So what I need, I add this gain KC to the system, so G1 to be K sub C times G. And so the KV of the new system is going to be this gain KC multiplied by the previous KV gain, which is a KV number, which is 1/2. This number I want it to be 10, therefore that constant KC is going to be 20 units to provide me with a much smaller steady state error. So that's the first stage. Stage number 2 is draw the Bode plot of this new system and then find the phase crossover frequency of the system. This phase frequency of G1, we're going to set it to be the gain crossover frequency of the completely compensated system. I mean the system that has the zeros and poles of lead and lag portion added, not just gain. Okay, and then we make sure the zero of the lag compensator, the lag portion of the compensator, which is this number here, this is 1 octave to 1 decade below this number that we find. That will give us T2. So let's do it step by step. So first thing we do, let me do it again from scratch for you here. So we first determine the transfer function. This is our transfer function with the gain of 20 Kc. And we determine again wide range of frequencies, and then draw the Bode plot, and then we do read on. Okay, so now it says in this system, which is called G1, you will find the new phase crossover frequency. Phase crossover means where the phase is negative 180. And if we determine this point, it is almost like 1.43 radian per second. We choose this number. And your textbook approximated this by 1.5. I don't know why, but that's how the textbook did it. Again, it does not really matter that much, but the way that your textbook approach at what frequency I have the phase of G1 to be negative 180, the answer of your textbook is 1.5, which actually you see is 1.43. Now it says go 1 octave to 1 decade below this to get the zero of the lag portion. And your textbook here went down 1 decade. If you go 1 decade, you're looking at 0.15. This is the zero of the lag portion, right? So from here, of course, you can find T2, which is should be 6.67. now, this is the portion that you borrow from the lead design. It says the maximum lead contribution angle, phase angle, is phi m. And for phi m, you choose whatever phase margin that the system needs, plus 5 to 12 degrees. By the way, pay attention that this system, if you look at the gain modified system only, the system that only has gain modification, no zero or poles added, is the system alone stable or not? Well, look, this is the frequency at which phase is 180. If I use that and go to the magnitude plot, what is my decibel? 10.3. And negative of that is gain margin. So what is the gain margin of the gain modified system only? Negative 10.3. Negative gain margin means what? The system is not stable. The other way is I find where the magnitude is 0, which is almost here, and then find the phase of the system at that frequency, which is this number, negative 208, and then I add plus 180 to it, which makes it negative 28 degrees. So the phase margin of this gain modified system is negative 28, and the gain margin is negative 10.3. So this system is clearly not stable. But now we make it stable, and we make it to give us the required phase and gain margin by adding a lead portion and a lag portion. The lag portion, we found the location of its 0. That's where we found it. This is where the 0 of it is. Now, in order to find the pole of the lag portion, which is at 1 over beta T2, we need beta. Beta and gamma, we chose them to be the same. So if I can find gamma, I found beta. And to do that, I used the formula that I had in the lead design. In the lead design, if you remember, I had that the maximum phase contribution of the lead portion is 1 minus alpha divided by 1 plus alpha. And here, this alpha that we introduced back there is the reciprocal of this gamma. So if I replace in that formula alpha by 1 over gamma, I get this guy. And from here, I can find gamma. So your textbook says phi m should be whatever that you need for phase margin, which is 50 degrees, plus an additional 5 to 12 degrees to compensate for adverse effect. And here, your textbook went with 5 degrees. Okay, so again, you can choose to be different, but your textbook says I want the 50 degrees required plus 5 degrees additional, and this is equal to the sine of this angle is equal to 1 minus 1 over gamma divided 1 plus 1 over gamma. And from here, your textbook found gamma, which is the same as beta, to be 10. And okay, now that you have beta of 10, you can definitely say the lag portion is what? Which was s plus 1 over t2 divided by s plus 1 over beta t2. This is equal to s plus 0.15 divided by s plus 0.015. So this is the lag portion. The gain C is also determined. The only thing left is parameter T1 for the lead portion. And here, that's how you determine the parameter T1. This is a graphical method that your textbook suggests. It says, find the magnitude of this uncompensated or gain compensated system at that frequency that you found, 1.5 in step number 2. Find the magnitude of it, and if we call it m, now pass through the point omega GC, which is 1.5, and m with a negative sign a line with the slope of positive 20 positive 20 decibels per decade. So what does that mean? Pass the line with positive 20 decibel per decade from point omega GC and negative M. What does it mean? So let's do it here over this graph. So first let's find M. So we go to frequency of 1.5, find the magnitude at that frequency, which in our case it is almost like 9.5, and then now we go to the points at the same frequency but negative magnitude, negative 9.5, which comes like here, and then through that point I pass a line with positive 20 decibel per decade. So to do that, I would like to zoom in a little bit here for you, and then first thing is, let me get rid of this data tip because I don't need it now. So now I'm interested in the point 1.5 and negative 9 decibel. It should be around here. If you forgot where 1.5 is, you can put the data tip back, okay? But it was here, so right below that, but at negative 9 decibel, 9.5. So you're looking at something like this, almost. And now through this point, you pass a line with positive 20 decibel per decade. So I insert a line, make sure my line has positive 20 decibel per decade. In other words, between two vertical lines, which is 1 decade, it goes up 20 decibel, like from negative 20 goes to 0, right? So this guy here has positive 20 decibel per decade, and I make this longer, so I go 2 decibels and 40, 2 decades and 40 decibel. That has the same slope. And now I make this line pass through this point, like this. Okay? And wherever it, now it says wherever it intersects the horizontal lines of negative 20 and 0 decibel, these are the locations of 0 and pole of the lead portion. So if I go back, find the intersection locations, one of them is here where it cuts to negative 20, and the other one is here where it cuts 0. Okay, and now these are the location for 0 and pole for the lead portion. The smaller number is the 0, the bigger number is the pole. And what are these roughly? So this is point 1, point 2, point 3, point 4 is this one. And then this number should, of course, be 4, 10 times bigger, because beta was 10, or gamma was 10. So this is 1, 2, 3, 4. So 4 and 0.4. Okay, so the lead portion of my compensator is S plus 0.4 divided by S plus 4. Now your textbook found 0.7 and 7 for these two numbers. I don't know again how, maybe because it uses negative 13 decibel instead of negative 9.5 at the gain crossover point, but I here find some different numbers. And of course this number is 1 over T1, so I can find T1, but it's not needed. So now I can say that my whole lead lag compensator, GC, is the gain KC, which was 20, times the lead portion times the lag portion. And the lead portion is this, and the lag portion was this one, if you remember. Don't know what's going on with my pen, but this is my compensator, and now I can multiply this by G, and now I can look at my new phase margin and gain margin. I leave this portion for you to do. So multiply GC by G. Okay. Draw the boolean plot for it and tell me whether it satisfies the gain and the phase margin of 50 degrees and 10 decibel or not. If it does, then life is good. Otherwise, we have to shift around these zeros and poles a little bit so that it satisfies it. But that's the overall procedure for a lead lag compensator. And final notes, which are important, the last two slides of this lecture is sometimes maybe both lead and lag compensators will satisfy the design requirements. Which one would you choose? Well, it depends, because each one has advantages and disadvantages. Lead compensator gives you basically a faster system, right? Larger bandwidth, faster system, smaller settling time, and more stable, of course. So if you really want a system that is fast, you have to go with lead. But you have to make sure that the inputs to the system do not have significant noise. Otherwise, it will magnify them and basically ruin the system's performance. On the other hand, if noise is so dominant that you cannot neglect it, then you want to use a lag compensator. So it depends on the quality of the input and how fast you want the system to be. So that is important. One other drawback of the lead compensator is lead compensator typically needs high gains. It will lead to large gains overall in the system. And large gains, when you want to physically create them, not just in simulations, a big physical gain means basically larger controllers, more space, more cost, more weight. And also many of the systems, they can only provide so much current, voltage, and input, and after that they would saturate. So it can lead to saturations as well. So if your system has a very high saturation point and the input does not have significant noise, you would use lead compensator to make the system fast and stable. If on the other hand, you cannot create such huge inputs and gains in the system, and there is noise, and you cannot simply filter it out and get rid of it, then you might go with the lag. Best option is typically if you can go with both, the lead lag. And you can see that in this example that we just solved. So if you can see here, the system on the left is the original system 1 over s times s plus 1 times s plus 2, which was not compensated. This is the step response of it, which shows relatively good speed but a lot of overshoot, and this is the steady state error in response to a ramp input, which is quite huge. Now here is a lead compensated version of the system, which lead acts like a PD controller, so it makes the system fast. And you see it settles down very fast on the step response. So the settling time is clearly much smaller than the original one. But look, the steady state error has not changed. Lead does not really work on this area, it works only on the transient part. Now if you do lag, kind of does the opposite. you see here that actually it made the transient response worse. You see that the oscillations are now slower and the settling time is even worse than the original one. But look at your steady state error. It is significantly reduced. And if you want everything with some compromise, you go with lag lead or lead lag. Look now. This is better than the original system, not as good as a lead only, but it is faster, the settling time is smaller, the overshoot is not as big, and the steady state error is also what? Smaller than the original system. Not as good as lag, but it's a compromise, right? So you can get some speed, some better steady state error. Not everything altogether, because these two are always in opposite directions. So with this one, you can do a trade-off between the two and you can gain from each one of them something. Hopefully, I could provide the material for you in chapter 7. Now, here is a small for yourself that if you want you can study about experimental determination of a model or transfer function that I mentioned several times in the lectures, but because of the time limitations, I did not have time to go through this example. But if you want, you can refer to your textbook and see just by passing a bunch of inputs, harmonic inputs, and measuring the outputs and drawing an experimental Bode plot like this, if we can infer the actual transfer function G, okay? So I mentioned some stuff about it, like how we can determine if there is a lag, how we can determine if the system is non-minimum phase, how we can determine m minus n, how we can determine the type of the system, and so on. But this goes a little more in depth by adding asymptotes and then finding the corner frequencies, which corresponds to the zero and pole of the transfer functions. So I'll see you in our next lecture and stay safe. Thank you.